Hello. Today we're going to work through some examples of damped periodically driven harmonic oscillators. To do this, we'll use several examples and then look at generalized cases. We'll also think about this in the differential equations perspective, where these are constant coefficient second order differential equations, and when they're driven, they're going to be non-homogeneous second order constant coefficient differential equations. So let's go ahead and start looking at this kind of example. So let's make sure things are lined up here. So we're going to do, as we say, damped periodically driven harmonic oscillators. If we remember the form, if we want to start from physics, right, F equals ma or mx double dot. But what are the forces? Well, let's say it's attached to a spring, so we have minus kx. This is Hooke's law. We also typically have some kind of drag, and drag usually goes like the velocity. So our standard example of damped harmonic oscillator looks like mx double dot plus cx dot plus kx equals 0. And this 0 means no driving force. We typically simplify this by dividing through by the m, and we write this as x double dot plus 2 beta x dot plus omega naught squared x equals 0. And this is going to make our life simpler down the road. Realize that in this case 2 beta equals c over m, where c is typically known as the drag coefficient. So drag coefficient. So beta equals c over 2m. And we also have omega naught equals the square root of k over m. This is our standard of doing a damped, right? Because we have a damping factor here, harmonic oscillator. If we want to add a driving force to this, we need some additional force, right? So we have the force of drag, we have the force of the restoring force or Hooke's law, and we need some driving force. So typically we'd add this driving force to say something like x double dot plus 2 beta x dot plus omega naught squared x equals, and we usually write this as f naught cosine of omega d times t. All right. In this case, notice that I've introduced a couple new variables. Here, omega is the frequency of the driving force, and f naught is the force of the driving force divided by m, so f naught equals, let's call this capital F naught over m. We're just going to scale it by the net mass. This just simplifies things. So let's see what we can do to try to solve this equation. All right. In particular, one of the homework problems that, or a good example problem that we're going to be working on is, let's assume we have k equals 1. Let's assume we have m equals 1. Let's assume we have f0 equals 1000. And let's assume wd equals 0.1 w naught. All right. It's helpful in these kinds of situations, especially once you gain some intuition, to think about what the answer is going to be. Just get an intuition for what the answer is going to be before you even solve. So, what's this actually going to look like? Well, let's think about this. Well, and we also need a c coefficient, and let's do a c coefficient of 0.01. So we have a small c. All right. And hopefully, we had a little glitch there in the recording, but hopefully it's back. So c equals 0.01. If I have these equations, right, I can also know that omega naught equals the square root of 1 over 1 equals 1. And that means omega d equals 0.1. And beta is just going to be 0.01 over 2 times 1. And this is just 1 over 100, so this is just 1 over 200. Okay, so what does this tell us right away? This tells us right away that beta is much, much less than omega naught. And you should know, or you should have this feeling already, that this means that this is an underdamped system. This means there's not much of a damping force. So if we have not much of a damping force, we know what this part of the equation is going to do if it equals 0. So, as you recall, an underdamped system is a system that does this kind of thing, where we have an oscillation and we have an exponential decay. Whoops, let's go ahead and get that in screen. So we have an oscillation. So this is my guess for the homogeneous part. What's going to happen, however, when we add the driving force? So when we add the right-hand side to this equation, well, we know that the natural part of the frequency is going to damp out after time, and as t goes to infinity, you're just going to be left with this driving force. So we're going to have the driving force, and what do we know about the driving force? Well, we know that the driving frequency is only 1/10 the frequency of the natural frequency. So this means you're trying to push it, if you want to think about it that way, you're trying to push it much slower than it would naturally want to go. So you think about something like someone in a swing that wants to swing back and forth, but you're, right, so you're in a swing, you want to swing back and forth, but you're trying to push way too slow, way slower than this. So this means you're going to be out of phase and it's going to be much slower. So the natural frequency is going to be something like this, but the driving frequency is going to be something like this, much slower. So that means adding, this is the behavior at infinity, well, at t goes to infinity, right? So infinity, it's going to look like this, and at the beginning, though, it's going to start at this natural frequency. So this is what's often called the transients, right? So we're going to have this short-lived transient behavior, then we're going to have this long-lived driven oscillation. So my guess for this situation is that we're going to have, so this is my driven oscillation. And so it's going to end up like that, but we're going to have this fast oscillation. So we're going to have something that looks like, let's say, something like this, right? Where we have this transient behavior. So we're going to have something like e to the minus beta t times the cosine of omega 1 times t. This is going to be something like the natural frequency plus some other something times the cosine of omega d times t. You notice that there's no exponential decay on the driving force, and so that's why at infinity this is going to dominate, and that's why we're going to have this additional part on top that oscillates here. So that should kind of be your intuition about what's going on. Let's see if we actually get that from the mathematics. So let's go ahead and get started here, and we can start with, well, we'll go ahead and start with what we've been doing here, 2 beta x dot plus omega naught squared x equals f naught cosine omega dt. So how do we solve this differential equation? Remember, we split this kind of into 2 parts. And that's, one, we pretend like this whole thing equals 0, right? That's going to give us one solution, and then we'll deal with this in a second. So let's first just pretend like we're going to get 0 here, and then we'll deal with this extra part. If this is 0, then this is just the constant coefficient second order differential equation. And we guess x equals e to the rt. And if x equals e to the RT, x dot equals r e to the RT, x double dot equals r squared e to the RT. Now we just plug that back into our equation here. And so we get r squared e to the RT plus 2 beta r e to the RT plus omega naught squared e to the RT equals 0. Remember, I'm making this assumption right now, right? I'll deal with that's not true here in a moment, okay? So let's make that assumption for now. And of course I can cross this out, cross this out, cross this out. And I say r squared plus 2 beta r plus omega naught squared equals 0. This is just a quadratic equation. When we have this quadratic equation, we just get r equals negative b, but negative, this is 2 beta, so negative b plus or minus the square root of, right, negative b plus or minus the square root of b squared, which is just going to be 4 beta squared, minus 4ac, which is just 4 omega naught squared, all over 2a, and of course a is just 1. So these are my r values. Notice that you see how clever my choice, well, this is why this choice is commonly made, of 2 beta here, is because I can rewrite this as minus 2 beta plus or minus 2 times the square root of beta squared minus omega naught squared all over 2. Where did this 2 come from? Well, I took the 4 out, and the square root of 4 is 2, so I can take the 2 out, and now I can just cross out these 2's, and r is just going to be negative beta plus or minus beta squared minus omega naught squared, square root. All right, so we're getting close. We're going to make another move here, and that is, if we look all the way back at the beginning, right, we see this assumption that beta is much smaller than omega. Well, if beta is much smaller than omega, then this quantity is going to be a minus, right? This is going to be negative because this is bigger than that. So we can always play a trick and say, we can always say a minus b equals minus b minus a, right? And we're going to do that same thing here. So we're going to do minus beta plus or minus 1 omega naught squared minus beta squared square root. And what's the square root of minus 1? It's just I. So we have minus beta plus or minus I omega naught squared minus beta squared square root. I'll just call this page 2 so we have that there. Hopefully that's clear. And we'll make a simplification here, and let's just say W1, let's just set W1 equal to W naught, omega of course, omega naught squared minus beta squared square root. Okay. So now we're getting somewhere. Let's keep going. And let's do, this is page 3. So our next move then is, remember we found r, so now we know our solutions. So that means x, and this is often called the complementary solution, so I'll call it x sub c of t, is going to equal c1, some constant we don't know, times, and remember we made the assumption that x is e to the RT and we found r, so we have to put it back, e to the minus beta plus I omega 1 times t, because this whole thing was r, plus c2 e to the minus beta minus I omega 1 times t. All right. We notice, of course, that e to the minus beta plus I omega 1 t equals e to the minus beta t plus I omega 1 t, and e to the a plus b equals e to the a times b, so this also equals e to the minus beta t e to the I omega 1 t. All right, this is just our rule for exponentials. With that being said, both terms are going to have this, so I can rewrite xc of t as e to the minus beta t times c1 e to the I omega 1 t plus c2 e to the minus I omega 1 t. We can rearrange this again. Remember that this can be rewritten in terms of sines and cosines, so equivalent solutions would be e to the minus beta t c3 cosine of omega 1 t plus c4 sine omega 1 t, or also equivalent c5 cosine of omega 1 t, well, plus c6. Those three are all equivalent forms of the same kind of thing. Now, if I was given initial conditions, for example, if I was given, let's say, x of 0 and x dot of 0, and there was no force, then I could just go ahead and solve this, and we'd be totally done with our solution. But this is not what we have. We have to deal with this extra part, and that's the driving force. So how do we deal with the driving force? Well, we need the particular solution, right? And so how do we get the particular solution? And let's go back and look at this page. Remember, again, we need this guy to deal with that. So whatever we put on the left-hand side of this equation here, we need it to get f naught cosine of omega t. So we're going to guess a solution of a cosine of omega dt plus b sine of omega dt. All right, that's going to be our guess, because that is going to give me derivatives that are sines and cosines. So let's go ahead and see what happens when we plug this in. So what's x dot? Well, the derivative of this is going to be minus omega dA sine of omega dt plus omega dB cosine of omega dt. X double dot is going to be minus omega d squared a cosine of this thing minus omega d squared b sine of this thing. Okay, now plug that back into this original equation here. So let's go ahead and try that. So we have minus omega d squared a cosine minus omega d squared b sine, right? This is just x double dot. And then we need the next part, which is going to be 2 beta times x dot. So this is going to be minus 2 beta omega d a sine plus 2 beta omega d b cosine. And then we need the last part, which is this part here. So we need plus omega naught times a cosine plus omega naught b sine. of this thing. And that whole thing has to equal F naught cosine of omega d times t. All right. So, next move is, let's go ahead and put this back. The next move is then to solve this part. The sines and the cosines have to stick together for one another. So, well, let's scoot that over just, well, let's scoot that up just a little bit so we can see it. So, I can rewrite this whole equation here as cosine of omega dt times minus omega d squared a. I'm just going to underline them here when I get rid of them. This guy plus 2 beta omega db plus omega naught a. So we got those three terms plus the sine terms, sine times minus omega d squared b, that's this term, minus 2 beta omega dA, which is this term, plus omega naught b, which is the final term. And this has to equal F naught cosine omega dt. All right. And we know that the cosine parts have to equal the cosine parts and the sine parts have to equal the sine parts. And therefore, minus omega d squared a plus 2 beta omega dB plus omega naught a, that's the cosine part, has to equal F naught. We also know that minus omega d squared b minus 2 beta omega dA plus omega naught b has to be equal to 0. Okay, so this means we have two equations and two unknowns. Our two unknowns are A and B. Everything else is known here. So we have two equations, two unknowns, and we could solve this, and I'm not going to solve this right now. This is a little bit annoying to solve, you can imagine. You can solve this for A and B. All right? So this will give you A and B, which remember were the amplitudes of the cosine part and the sine part. All right. I'll simplify this for you. I'm not going to work this out for you. If you want to, you can work this out as an exercise. But if you work this out, you're going to get an amplitude. You're going to get something like the particular solution is going to be equal to, well, let's call it, let's call it, I'm going to call it gamma, just so we have something there. This is the amplitude of the oscillation, so this is going to be gamma cosine of omega d t plus, let's call this delta. Okay, so remember, sines and cosines can be written in this way, just like we rewrote here in the different forms. So I chose to write in this form. If I choose to write it in that form, and I go ahead and carry out the solution for A and B, so I'm going to use this solution for A and B. I'm also going to use what's called the harmonic, H-A-R-M, harmonic addition. harmonic addition theorem. Go ahead and Google that if you want to know more information. This is just basically tells you exactly how you can get C5 and 6 in this equation from C3 and 4 in that equation. And if I use the harmonic addition theorem, I'll find that gamma equals F naught squared divided by omega naught squared minus omega d squared plus 4 beta squared omega d squared square root, and the phase is going to equal the inverse tangent of 2 beta omega over omega naught squared minus omega d squared. Yeah. So the inverse tangent of this. All right. These are helpful equations. These are also where resonance comes from. You'll notice that this particular solution tells us what the amplitude of the oscillating frequency is as we go to infinity, right? So if I look at gamma, or let's say I look at gamma squared is going to be a curve, something that looks like this, where this is the driving frequency and this is the natural frequency, and you're going to have a resonance. So if I'm given exactly the same force, I'm going to get larger oscillations when the driving frequency equals this frequency. And hopefully you can see that in this equation. When this equals that, this part is going to be 0. And if that part is 0, then the square is going to be 0. And so this part of the equation is going to be minimized. And 1 over a minimized thing is a maximized thing. So that's where the peak is. And if you look at this phase, you can find a phase that looks something like this, where you have omega d and you have omega naught. So when your driving frequency is slow, your force goes like this. You're 90 degrees out of phase, right? This is 90 and this is 180. And when you're fast, you're 180 degrees out of phase. Yeah, this is squared. So these are nice equations to have, but you notice you don't need them, especially if you have specific examples. And this is what some of the homework might be is, remember I gave you specific examples for, we look way back here at the beginning, right? Remember omega d was 0.1. So omega d was way down here. So we expect to get some amplitude here, and some phase here. Okay. So let's go ahead and put this all together. And what's our full solution going to be? Our full solution to this guy, remember, is the particular solution plus the complementary solution. So this is going to be e to the minus beta t times, let's say, yeah, times, well, we'll write it like this. C, 1, 2, 3, 4, 5, C5 cosine omega 1t plus delta, or we call this C6, let's call this C6, plus gamma cosine omega d t plus, we're going to have a delta here. All right, so let's then whoops, look like we have another small glitch, but that's okay. Let's go ahead and keep recording. And oh, I should be careful here. Notice that this is a minus sign here. This is a minus sign here. And anything else that I did that, oh yeah, this is omega d here. Okay. So it looks like everything else is all right. Notice, I shouldn't hide this from you. Notice that I've used a slightly different definition. Notice that this is a plus sign here in the way that I've defined it, and notice that this is a minus sign here with the definitions that I gave. Of course, you can absorb a minus sign into these terms, but just notice for the equations I've given so far, this is the way these things are defined. So this is going to be our final solution to this equation, where we have all the caveats. Remember what beta equals, omega 1 equals, right, and gamma equals from before, right? So, and this is, remember, this is often called the transients, and this is called different. Sometimes this is called the response, but notice there's no decay factor. So if you're asked for something like what is the solution as t goes to infinity? As t goes to infinity, right, this minus beta is going to die out. So all you'll have left is this term. Okay. So let's go ahead and look at this kind of situation. So for our particular case, going way back to the beginning, remember we had omega naught equals 1. We had f naught equals 1000. We had omega d equals 1 over 10. And what was the last thing we needed? Let's see, omega d, beta, I think that's, oh, and we had beta equals 1 over 200. Okay, so those are the things we need. All right, so let's go ahead and try to solve everything we have here. Well, the beta part is easy, right? So that immediately gives us this beta. So we have beta. Remember also omega 1 equals the square root of omega naught squared minus beta squared. This is just going to be 1 squared minus 1 over 200 squared. Right, this approximately equals 1 as well. So we have omega 1, so that gives us this. Then the only thing we need to worry about is C5 and C6. If we actually want C5 and C6, then we would use the initial conditions. So we need more information to determine what C5 and C6 are. So we could think of a situation, for example, well, let's make our lives easy and say x of 0 equals 0 and x dot of 0 equals 0, right? Generally speaking, these are called x naught and v naught, right? So you could be given other equations there, right? But let's just make our lives easy in that situation. So if we're given that equation, then we can actually solve for this, right? Because we would say x of 0 equals 0 equals this whole equation here. And we know what everything in this equation is. And then we'd have x dot of 0 equals 0 equals, and we take the derivative of this whole equation and solve for those numbers inside. All right, so hopefully that procedure is fairly clear in these situations. All right, and if you do this, you're going to get the solution we had before. Notice that if you don't care about the transients, if you don't care about this part, then your life becomes much, much easier. You only care about this part, and this part, we don't even have to worry about the initial conditions really. We just have to worry about the parameters, and we can solve those parameters as we did here, or you can directly solve them from this equation in the box. All right, and that will give you the behavior as t goes to infinity. So this video is running a little bit long, so we're going to go ahead and call this the end of this particular video. We'll do another video on several specific examples. Note now that we have this worked out in general, we'll do some specific examples and look at how the trajectory actually looks next. Thank you very much.